Hi, my name is Benjamin Freeman Wilson, and today we're going to be talking about how to implement a grammar in Langium. So if you watched the last video, you will have learned a bit about how to actually set up a default Langium project using the Yeoman generator and the Langium generator extension. We went over the defaults, showed this hello world program, which is written quite simply, and we wrote a simple program in this language as well. But really, we're interested in writing our own language. So in this one, we're going to be going through how to write a grammar from scratch, piece by piece. Now, the first part of your grammar is always the grammar declaration, which is a keyword here that indicates the name of your grammar. Now, for this example, we're going to be writing the mini logo grammar for the mini logo language. Now, mini logo is quite akin to the original logo programming language, but miniature, which is akin to, in turn, Turtle, which followed later in Python. So it's just a simple language that allows providing drawing instructions that can be adapted to some drawing context. So in this case, we're going to call our grammar mini logo. Great. Now we have an error here. Let's see what this is. We're missing an entry parser rule. So what we can do is we can add an entry point with the keyword entry. Now we're going to call this model, and we're going to indicate that a model has two things. It has an array of statements, and it has an array of definitions. And really, this is an OR, but we're going to do 0 or more of any of these. So the plus equals is a way of doing multiple assignments, so we can have any number of statements or definitions in any order here for a model. It makes sense. A model for our language can be composed of definitions, which are going to look like functions, and just raw statements. Okay, now we're going to actually write the statements themselves. So we're going to declare another rule, just like our model rule, but it's not the entry. It's just a standalone rule here. And it's going to have two subrules as its body, command and macro. Now, command is going to be another rule, and it's going to be in turn composed of four other rules: pen, move, color, and for. Pen controls moving a pen on and off a canvas. Move is going to indicate moving around on that canvas. Color is going to set the color of the stroke of the pen, and for is it's going to be our only control flow in this language. It's just a simple for loop. Now we're also going to write macro here. This rule is going to have a definition name that's going to correspond, or sorry, this rule is going to have a cross-reference to a definition. Now we haven't written definition up yet, but you can see it was already listed up here. This is going to be kind of like a function, but in this language we refer to them as definitions. Now this syntax here with the square brackets is a cross-reference. It allows us to take a pre-existing definition that was already listed in our language, like here, and be able to link against it. This is a really powerful topic, so we don't actually have to put a keyword in here and then look it up later. We can trust that this definition will actually be a reference to a previously defined instance of a definition in our language. And this is a pretty handy feature. Okay, then we're also going to wrap our expression in parentheses, and then we're going to say any number of arguments here. Well, some list of arguments will be contained, and we're going to do this kind of style here with them being able to be added to each other. Oop. Put a star there, and then make this whole thing optional. Now, and then, forgot the very end here. I want to cap this off. So what this is doing is this is just wrapping some concrete syntax here where we just have parentheses. They don't actually add any meaning in our AST, but they're used to structure how we parse things so that when we see an instance of expr, we're going to collect it into an array of arguments, and we can have optionally 0 or more additional expressions, each separated with a comma. So it's just an array of arguments that are going to be passed in to a macro. Okay, now the actual definition itself starts with the keyword def. Its name is going to correspond to ID. It's a terminal we haven't written yet. We'll do that in a little bit. Another opening block, and I'm just going to copy this one over. It's a little faster than typing. And the rest like this. Now, again, we have the same kind of style of syntax here for the grammar, where we have at least one param, potentially, followed by any other additional number of parameters. Oh, sorry, correction. It could be 0 or more params, and then followed by a block. Now, a block is something that is referred to as a fragment. We'll bring that over here too. Now, a fragment is a special kind of instance of content that can be added into the body of a rule, like def, but it in itself is not a rule. This doesn't produce an object. It's just a reusable piece of grammar logic. So this is particularly helpful for factoring out common patterns because this block is going to come up at least one more time later on. All right, now we're going to write another rule, name ID for parameters. Parameters have a name property, and that's going to be associated with the ID terminal. So let's actually bring the ID terminal over here too, because that will be nice to see how that looks. So this is the terminal syntax. We start with the keyword terminal. We give the name of the terminal. Ideally, we like to go all caps, but this is by convention. And then you can optionally indicate the return type. And the return type is going to correspond to a type that exists in TypeScript. So keep that in mind. In this case, we're just going to return a simple string. See, it's just a lower or uppercase starting symbol, our character with an underscore, and then 0 or more words and underscores attached after. So it's just a simple JavaScript regular expression. Very easy to understand in this context. Okay, now let's go add in some of these commands that are missing. We want to get those in place. So first one is pen. Pen starts with the pen keyword, has a single argument of mode, which is a constant of up or down. That's it. So it's just two types essentially. We also have move. Move is very similar, but it uses expr again. So move has an x and a y component, both expressed as an expression. We also have for loops, indicated with the for keyword. Now, the syntax of for in this case looks kind of like this. So say for x equals 0 to 10. This goes 0 to 10. So it's a very simple design, and then block, because of how that's designed, would look like this, with some number of parameters are broken down across lines. So our for loop is not in the traditional style. It's a very simplified design, but it just gives some form of controlled looping iteration that we can do. So again, this uses expressions. The starting expression for the assignment to this parameter, this variable, and this boundary expression that it can go up to. Now, keep in mind this is one directional. It's going to just increment up, so you can't go down. And also, this is one of the few cases where we actually define something, like a variable that we're actually going to be referencing. This also comes up in the context of a definition body, where we have parameters that are bound to arguments. Okay, and then we have one more here. We also have the color command. The color command is a little loaded because it is overloaded. It is a single function, essentially, or macro if you still want to think of it like that. And it wants to pick up one of two types of structures. The first structure is a series of 3 arguments, a red, green, and blue argument. Oh, that's interesting. This one has a space here. Got to make that consistent. All of type expression, or it can be an ID. So basically, this is a very crude way of saying it can be probably what would be a color like blue, red, white, yellow, purple, etc. This isn't strictly enforced here, so it's up to the user. You could also type something that's not a color. And also hex. Hex is not listed, so let's go ahead and add this terminal too. And there it is. Also returns a string, and it has a totally different sequence. It just looks at any number of decimals, or A through F, lower or upper, proceed with the pound sign. Notice it's doing 1 or more with the plus. We should really be doing 3 through 6 to be more specific here, or 3 or 6. But we're just doing this very generally right now, so again, this will suffice. Keep in mind the order, by the way. Terminal order is very important. This is not the same as writing this. Terminals will be matched first come, first served. So if you want a terminal to take precedence over another terminal, you really want to match this first. In this case, it's not too bad because we have a pound sign here. This isn't going to be captured by the second terminal, so we're okay in this context, but really is important to keep in mind. Okay. Now we have expressions. So right off the bat, we're going to do expression add. This seems a little funny, but we're going to explain this in a second. Normally you would do something like expression and then maybe do like expr plus expr or a bin op or something in this case and be able to actually express binary expressions, but the problem is that you have left recursion, and Langium is built off of the Chevrotain parser building toolkit, and that's a top-down parser that's going to construct. So we have issues with handling left recursion. Again, this is LLK, so we only have k tokens of look ahead. We can't determine this. So we're going to need to rewrite our grammar to actually produce a parser that isn't going to just fail on us. So we're going to start to preserve our order of operations with the least significant operation, in this case with addition. And then we're going to express a rule. Now, get ready for this. We're going to express a rule add that infers an expression. What this means is that this parser rule will produce an object of type expression. It will not produce an object of type add. Normally, the parser rule also dictates the name of the node that's going to be produced in our abstract syntax tree. In this case, we're making an exception. We're saying it's inferring something else. This lets us keep exprs kind of similar, even though our rules are different. Now in here, we have some more funny syntax. We have mult. We're going to define that soon. That's going to be multiplication and division. And then we have something in here. Now, this is an action, this bit in the curly braces. It's using a similar infer keyword, but it's a little different, and the context is different. What it means now is that in the case where we parse the multiplication, the parser rule mult succeeds. And we have 0 more of plus minus followed by any other multiplication. Then we have a binary expression, and we know this. So what we're going to do is we're going to change in the body, for this case, we're going to change the object to a binary expression, and then we're going to take E1, we're going to add the property E1 to this binary expression object, and we're going to set it to what we have currently parsed, which is going to be mult. That's all that this is doing. So this lets us handle the case when we have just mult, as in, binary expression with just, or just, some single case. But we'll explain here, because mult in turn is going to also extend onto a primary expression. So sometimes we'd have just one, and sometimes we're going to have an actual binary expression as opposed to a singular expression. Okay. And it also goes without saying that this add rule is not really just add, it's just addition and subtraction combined. And as you may have guessed, this is going to be about the same with multiplication as well. It's also multiplication and division. Notice the pattern is identical. I could even shorten this here really quick so you could see it, how it lines up. It's actually pretty much the same exact style, different operand or operators, and but we're still making this action here for this case, where we're detecting if we have actual binary operation going on. We're going to go ahead and change to a different object. Okay, cool. And now we're still missing some stuff. So lastly, at the very end of this chain that we built, which preserves order for operations, we're going to want to also define a primary expression itself, which is composed of 4 additional rules as well. And we're just going to copy all these rules in comments too, because it's a little easy to read through them. The primary expression is composed of a literal, which is a literal integer, a reference, which is a cross-reference to some parameter by ID. This is very nice because we already have parameter referenced in a couple of cases here for for loops and defs. I mentioned this before. So now we don't have to copy these in. We just get a nice cross-ref built right into our grammar. Grouped expressions with parentheses, we just nest an expression inside some parentheses. It's balanced. And we have negated expressions, just a really simple case that we've implemented here. All right. Now let's double check and let's see what else is missing from our grammar. It looks like we're missing a terminal here. So cannot resolve reference to abstract rule name int. Right, we need to add an int terminal. So this one's going to be pretty easy. We're just going to recognize integers that yeah, just regular integers, positive or negative, but no decimals, at least not for this case. We could, but we're not implementing it here. And technically we are complete with this grammar. However, we're missing something we want to add. We want to indicate some hidden terminals, specifically how we handle whitespace, because our language is going to be whitespace insensitive. So we can start by writing a hidden terminal, WS, to indicate whitespace. So basically any number of one or more spaces is going to be ignored. It's not going to have any significance in our language. This means if we had something like 1 plus 1 is going to be the same as 1 plus 1, or, many tabs 1, because a tab will also count as a whitespace character. So some languages you may not want this if your language is Python based, and if so, you'd have to do a little bit of extra changes here, but we're going to go ahead and work with the whitespace insensitive implementation. We also are going to add a hidden terminal for multi-line comments. So this regex will allow us to just match a brace, but it won't do nesting necessarily, by the way, because it's not actually doing any state here. I mean, this is just a regular expression, so it can only match a regular language. And a case of nested curly braces, or sorry, nested block comments is not regular. We need a stack to support that. And you can actually do this in Langium, but for this case, we're going to keep it just really simple. We're going to assume our multi-line comments are not nested. All right. And then we're going to also recognize classic C-style comments, which are just some pair of slashes followed by anything that is not the end of a line. Great. And now we are essentially set, but the final test, the real litmus test that tells us that we didn't screw something up along the way, is to actually run npm run langium generate. And we should get this out, but if you see green here, you're good to go. Specifically, we want to be seeing that the config is read, generated files have no problems, and we get a text make grammar. This comes with it. This is for syntax highlighting. No issues here. We also want to be sure that build runs okay, but here's the catch. This was a Hello World project, and this was a Hello World grammar, and this produced a particular structure that was specific to that Hello World grammar. So when we run npm run build, it's not going to work because there's quite a lot of stuff that has changed, and this is actually okay. We're going to be making this change over a series of videos. Specifically, in the next video, we're going to be tackling, which one was it here? There was one on validation. This one here in the validator. We're going to be jumping into the validator, which is the next step, and we're going to be changing validation because this was fixed to nodes that no longer exist in a structure of our language. So we need to change this. All right. Hopefully this video has been helpful for you, and we look forward to seeing you in the next one where we'll talk about implementing a custom validator for your Langium-based language.